Hello and welcome everybody to NASA's Jet Propulsion Laboratory in Pasadena, California. We're here today to talk about NASA's next mission to Mars, the InSight lander. We're a little over a month from launch, so we're getting pretty excited here. I'm Jari Cook of JPL's Media Relations Office, and I'm going to be your moderator here for the news conference today. We've got a great group of people who will help tell you what makes InSight special. So I'm going to introduce them to you right now. So right here we've got Bruce Banerdt. He is InSight's principal investigator. Next to him is Tom Hoffman. He is InSight's project manager. And in a very special location at JPL, where we try and test our robots in a Mars-like environment before we actually send them to Mars, is Jaime Singer. She's InSight's instrument deployment lead. To kick us off today, we have a very special pre-recorded message from Thomas Zurbuchen, the Associate Administrator for the Science Mission Directorate at NASA headquarters. He's going to tell us how InSight fits.
Good afternoon. I'm Thomas Zurbuchen.
Okay.
Administrator for NASA science programs here at the agency's headquarters in Washington, D.C. Today you'll hear about our next journey to the Red Planet, a lander called InSight. The first mission to study the interior of Mars, something never done in the exploration of this planet. A dictionary definition of InSight is to see the inner nature of something. InSight will do just that. In essence, it will take the vital signs of Mars, its pulse, temperature, and much more. We like to say it's the first thorough checkup since the planet formed 4.5 billion years ago. We've been studying Mars with orbiters, landers, and rovers for years now, discovering and learning much with each mission. We haven't landed on a planet since 2012, and now we're ready to go back. This mission also has many firsts in science, technology, and even in location. It's the first interplanetary launch from the West Coast, but this is more than just a Mars mission. InSight can teach us about the formation of our Earth, our moon, and even rocky planets in other solar systems. There's something we always remind ourselves here at NASA. Exploring Mars is really hard. In fact, nothing is more difficult in robotic planetary exploration than landing on Mars. The U.S. is the only nation to successfully land on Mars. Still, Mars always presents a huge challenge. This mission is the culmination of the dedicated work by NASA along with industry and international partners. We're proud to have the international team working with NASA to explore Mars. And as we plan to return to the moon, we'll expand our partnerships with industry and other nations to explore our lunar neighbor and advance our missions to Mars at the same time. NASA science strives to impact and inspire the next generation, and we will use every opportunity to engage everyone in our innovative work and help continue us all to discover today and for decades to come. Enjoy today's briefing, and I'll see you at launch. Go InSight.
Okay, all right. Well, thanks to Dr. Zurbuchen for that message that helps us understand how InSight fits in context with NASA's history of exploration. So we're going to have a discussion here at JPL. Then we're going to open it up for questions, so we'll take questions here. And then we also have some reporters on a phone line. And for those of you on the media line, if you want to ask a question, press *1. We're also taking questions via social media, so you can use the hashtag #AskNASA. All right, so I'm going to turn it over to Bruce.
Okay, thanks, Jari. So I don't think you can imagine just how excited I am, not so much to be here today, but to be 36 days away from launch of the InSight mission. This is something that I've dreamed about and devoted my career for 30 years now. Been trying to refine this mission concept and get it ready to go, and finally we're right on the verge of taking off for Mars. So a little bit about the science on InSight. The goal of InSight is nothing less than to better understand the birth of the Earth, the birth of the planet that we live on. And we're going to do that by going to Mars, which seems a little bit counterintuitive. So if I can have the first image. Planets are very, very complex objects. So, you start with a solar nebula, which is kind of a uniform a cloud of meteoritic material, which is not a very interesting rock. It's kind of gray and featureless. It accretes into these bodies, some larger, some smaller, and then it goes through a process that we call differentiation. It goes from a body of this uniform material into a very diverse and complex body that has a core that you can see at the center of each of these bodies. Its core is made up of dense iron and nickel. It has a rocky mantle surrounding that core, which is made up of rocks, but they're rocks that are higher density and of a crystal nature that you don't really see at the surface because it only exists under pressure. And finally, a crust. And that's the part of the planet that we interact with, that we live on, that has concentrated all the materials that are the building blocks of life. And so how we get from a ball of featureless rock into a planet that may or may not support life is a key question in planetary science. And these processes that do this all happen in the first a few tens of millions of years, which is just a few seconds at the beginning of the life of a planet that lasts 4.5 billion years. So we'd like to be able to understand what happened, and the clues to that are in the structure of the planet that gets set up in these early years. Except for the Earth, all that information has been obscured by plate tectonics, by vigorous convection in the mantle, and so we're kind of at a loss to see on the Earth, what's the evidence for what happened in those early years. But we can go to Mars, and Mars is a smaller planet. It's less active than the Earth, and so it has retained the fingerprints of those early processes in its basic structure, the thickness of the crust, the composition of the mantle, the size and composition of its core. And by mapping out these boundaries, these various different sections of the inside of the planet, we can then understand better how the planet formed and how our planet got to be the way it is, where we can actually live and play and have a good time, whereas other planets like Mars itself and like Venus are places where life really would have a hard time surviving. So we're going to go to Mars, and in order to do that, we need to be able to probe deep into the planet, not just down a few inches or a few feet, as we have done with some other missions, but all the way down to the very center of the planet, roughly 2,000 miles beneath the surface. And we're going to do that with 3 investigations. The first is a seismometer. Have the next slide. The seismometer is a very, very sensitive, sensitive is really an understatement. It's exquisitely sensitive device for measuring the motion of the ground. And when I'm talking about motion, talking about vibrations that have an amplitude sort of comparable to the size of an atom. So these are waves that were generated maybe by a marsquake on the other side of the planet, have traveled all the way through the planet, getting their waveform modified as they go through the planet and picking up information about the deep interior structure, and then we are able to pick it up when it comes back up to the surface under the seismometer. And in order to do that, not only do you have to have a very sensitive device for measuring those motions, but you have to protect it from everything else that might affect it. And so you can see in this picture, we have the sensors at the center that are doing the measuring, and then we have several different layers of protection. It's sort of like a Russian doll where you open it up and there's another layer and another layer and another layer. And finally, in the inside, you have these very coddled protected instruments. And so this is our basic, our really key basic instrument for probing the inside of Mars. The next investigation is the RISE experiment, which is what we call a radio science experiment, and it uses the radios on the spacecraft communicating with a deep space network on Earth, which are those huge radio dishes that communicate with the spacecraft. And by using the frequency shift of this communication, we can track the location of the spacecraft with an accuracy of just a handful of inches, which is an incredible feat. At 200 million miles away, we can tell where that spacecraft is within a few inches. And as the planet rotates, with the spacecraft sitting on the surface, we can watch that rotation and figure out the direction of the North Pole of Mars and watch that pole wobble over the course of the Martian year. And the size of that wobble and the frequency of that wobble is connected to the way that the core of the planet interacts with its mantle, and we can actually derive the properties of the core, its size and its density, from the characteristics of that wobbling. And the third experiment that we're going to do on Mars is a heat flow experiment. We're going to measure the amount of heat coming out of the planet. And we're going to do that in a very kind of a novel way. If I had the next slide. It's novel in a sense, but it's not new. This is something that we actually did on the moon. And we do that by pushing a temperature probe down beneath the surface of the planet. In the case of Apollo, they pushed it down several feet below the surface, and you measure the temperature as you go down below the surface. And it's going to increase slightly with depth because a planet is hotter at depth than it is at the surface. It only increases maybe a few hundredths of a degree as you go down that distance, but we can measure that and extrapolate it down. So if you have an astronaut on the planet, you can do this in maybe 20 minutes or half an hour. But if you want to do it robotically, you have to get a little bit more clever. So the next image that we have, I believe, is a video. No, okay, so this is an animation that shows what we're going to do. We have something we call a mole because it burrows down into the surface. And what it is it's a little torpedo about this big with a hammer on the inside that gets wound up on a motor, and it goes over and over again about every 3 seconds, hammers this thing down, and finally it should go down about 5 meters or so, which is about 15 or 16 feet, and it pulls behind itself a cable that has temperature sensors along the cable. So instead of only going down a few feet, we think this remote probe, we can actually go down about 15 feet, which gives us a better baseline to measure the temperature increase with depth and be able to estimate the amount of heat coming out of Mars. And that amount of heat is tied to the geological activity of the planet. It's the heat engine of the planet that drives volcanism, it drives tectonic activity, it drives mountain building. So all the geological processes that happen on a planet are driven by its heat engine, and we want to measure sort of the vigor of that heat engine. The next video shows a little bit more about how this thing works. This is a field test that we actually did in the Mars yard here at JPL. You can see the mole there in his hand, and there it is halfway down. I don't know if you can hear the sound, but it goes click about every 3 seconds. And if you look real closely, you can see it move about a millimeter at a time. And so it has to do that about 10,000 times to get down to depth. But we've got lots of time to wait for it on Mars. And so this is what's going to tell us just how active the planet is after we get to Mars. So that's kind of an overview of the science that we're doing. And in order to do that science, of course, we have to get to Mars, and we have to put these instruments in a place where they can make their measurements. And Tom Hoffman, the project manager, is going to tell you a little bit about how we're going to do that.
Thanks, Bruce. Yeah, I haven't been working quite as long as Bruce has on this project, but it's been about 7 years for me, so it's been also a journey of passion that I've had. So for the past couple of years, we've been putting together the spacecraft at Lockheed Martin in Denver. They're the spacecraft contractor building the flight system that'll make Bruce's dreams a reality. So we've been doing that for the last couple of years. The last fall, we've been doing the environmental testing, so simulating the Mars environment that we're going to see once we get to Mars, doing all the testing necessary to verify that the system is fully ready to go. Just recently, we actually shipped the spacecraft to Vandenberg Air Force Base. As you heard from Thomas Zurbuchen, this will be the very first interplanetary launch from the West Coast in California. So we're breaking the monopoly that the East Coast has had on interplanetary launches with this launch. If we go to the first image, this is a picture of us, video of us arriving in Vandenberg on a C-17. Inside of that white container is our spacecraft. So it's been carefully secured in there, and this is at Astrotech facility at Vandenberg. We have the spacecraft inside of what we call the bird cage. We will be having a media day on April 6th that if you're part of the media, you're invited to come and actually see this in Vandenberg. So you'll see that spacecraft as it's in its final preparation before we actually launch. If we go to the next image, this is what we hope we will see on May 5th. This is not our launch, obviously, but this is an atlas from Slip 3 at Vandenberg. So you can see it's a beautiful area. I'm really hoping that we have a clear day like this. We'll see. It's May in the middle of California, and we're also launching at 4 a.m., so it'll be a little bit dark. We have an animation that we can show you if you run this. One of the cool things is if you are in the Southern California area, you'll see a slowly expanding blue circle. This is sort of the view angle, so depending on where you are in Southern California, you'll be able to see the spacecraft at various points along its ascent as it heads off on its way to Mars. This should be quite spectacular because it is early morning hours, so it should light up the sky and be very visible throughout pretty much all of Southern California, even down into Mexico. At some point, it'll disappear because it'll get too high up in the sky for it to actually be visible, but it should be spectacular. If you happen to be up and nothing better to do at 4 in the morning, please take a look at your back window. And so one of the other things I mentioned is we are an evening launch, so if we run the next video, you'll get a better idea of what it will look like, hopefully on a clear day. If we can run that. So it'll be evening time. We'll have the tower all lit up. We'll send the rocket on its way, taking the spacecraft to Mars. This is an Atlas V. It's a very capable rocket. One of the questions we often get is, why are we launching from the West Coast? Originally, the spacecraft was designed for a smaller rocket that we built on Heritage, Delta II. We're on an Atlas V, so that gives us enough throw capability to get to Mars from either the West or the East Coast. A little less congestion on the West Coast, so that's why we chose that. On the way to Mars, we do a series of trajectory correction maneuvers, the TCMs shown here. What that does is it actually allows us to arrive at Mars on November 26th, regardless of which day we launch during the launch period. I've been told and reminded that that's the Monday after Thanksgiving, so it's Cyber Monday. So if you're all shopping online and you're interested in your shopping at 4 a.m. in the morning, online you can actually watch the video of the launch and even after the launch period of time on your own computer. So once we get close to Mars, we go through what we call our entry, descent, and landing phase. So that's where we actually go through the atmosphere, about 7 minutes, also referred to as 7 minutes of terror, because that's when the project manager and maybe even the PI are completely terrorized by all the possible things that Mars could throw at us. As Thomas Zurbuchen said, Mars is always throwing us a surprise. Hopefully we won't get any surprises on our landing day, but you never know. We've done a lot of testing, a lot of analysis to make sure we've done everything we possibly can to land safely. And so I believe that we're going to do that. If we show the next video, that will show actually what happens during that phase. So we're starting at about 12,500 miles per hour when we hit the atmosphere. We slow down with the heat shield. Then we throw a parachute that further slows us down. We eventually drop the heat shield, as shown here in just a second. And then we acquire the ground with a radar that shows us just how fast we're moving as well as how far we are from the ground. Once we get close enough to the ground, we let go of the parachute and the lander drops. Then it starts firing thrusters as it gets closer to the ground. As it gets all the way to the surface, we're going about 5 miles an hour. So in 7 minutes, we've gone from 12,500 miles per hour to about 5 miles an hour. And we land, and the legs are shock absorbers, so essentially they absorb the remaining energy there. And that gets us through our entry, descent, and landing. But unlike a lot of missions, that's not the end of entry, descent, and landing for us. We actually have the 3 elements on the lander deck that we then have to take from the lander deck and put it onto the surface of Mars. So I consider that sort of our second EDL, and that takes a lot longer than 7 seconds. That takes about 2 months to finish that operation. We've been working on that as well to understand that, how well that's going to work. We have an animation that we can run that shows you how that works. This takes about 1 minute, so that would be great if it was 1 minute, but like I said, it's about 2 months long. We have to go through a process of understanding what the terrain's like before we even start the deployment. Then we'll place the size down. We have to make sure that it's in a very good position and area for it to get the measurements back that Bruce and the rest of the science team needs to make sure that we get the science that we want. And then we take this wind and thermal shield and place it over the seismometer. That basically is intended to duplicate what we do on the Earth. On Earth, seismometers are typically in vaults that are climate controlled, well under the ground, no pressure changes, very little environmental impact. On Mars, we don't have any of that. We're out in the middle of a plane with wind and pressure and all kinds of stuff. So that wind and thermal shield actually tries to emulate as well as we can that vault. After that's done, as you saw, the heat flow and physical properties probe gets placed down, and then actually it will start the process of hammering into the Mars itself, and that takes about a month longer to do that process. So we've been practicing that, as I said, for several years now, trying to get the process down to make sure we fully understand how well that's going to work, all the challenges in that, trying to beat down those challenges and make sure that we have a solid program there. And so to tell you more about exactly how we've been doing that and where we stand with that, we have Jaime Singer over in the ISIL lab. And so I'm going to hand it over to Jaime. Go ahead.
Thanks, Tom. Welcome, everyone, to the In Situ Instrument Laboratory here at JPL. This is a facility where many of our previous Mars missions have prepared to do Mars surface operations, and that's what we're doing here with InSight. So this lander behind me is the InSight deployment testbed. It's not the real flight lander. That one's at Vandenberg Air Force Base, getting ready to launch. This one's more like the stunt double and allows engineers like me to test things out with the lander prior to doing them with the flight lander that's going to Mars. So it has representations of much of InSight's hardware and allows me to point a few things out to you. So you can see the lander here in the deployed surface configuration. The surface configuration with the solar arrays deployed. So there are 3,200 solar cells on the solar arrays, and those charge InSight's batteries and provide power to all of the components on the lander. InSight's going to land in a new place on Mars that none of us have ever seen the surface from the surface before. So like any tourist, we're going to want to take some pictures. InSight has 2 cameras for that purpose. So we've got the instrument context camera right here on the body of the lander under the deck. And then we have the instrument deployment camera right here on the robotic arm, which I'll talk more about in a moment. This camera on the body of the lander will take the first image that we get back from Mars. So of the 3 science investigations experiments that Bruce talked about, I'm going to first point out some of the hardware for RISE. So RISE is the radio science experiment. It uses 2 antennas. One is right here, and the other one is on the other side. These antennas are fixed on the lander deck and point towards Earth. A fun fact is that it takes a signal sent from InSight anywhere from around 3 minutes to 20 minutes to be received on Earth, depending on where the planets are in their orbits. Okay, so now for the really exciting part, the instrument deployment part. So you can see we've already deployed one of our instruments today to the surface. So one thing is that we're going to use the cameras, not just because it's cool to see the surface of Mars, but also because they allow us to select a site in front of InSight to deploy each of the instruments that are within the instrument's constraints. So we're looking for somewhere that doesn't have a slope that's too high, so roughly pretty flat, and is free of obstacles relative of sizes that are relatively small compared to the size of each of the instruments. So you can see here the seismometer is deployed. Right now it's under its wind and thermal shield, which has already been deployed on top of the seismometer. This keeps the seismometer cold throughout the Martian night and also protects it from wind during the day. So lift this up, you can see the mylar and chainmail skirt that goes over obstacles to seal up any gaps. So now you can see here, this is the seismometer in the deploy configuration. Today it's in our sandbox, it's deployed on this crushed garnet surface. That's something we use in the testbed to simulate the Martian surface without generating too much dust. The seismometer is tethered to the lander. So you can see the tether here. That's cabling that allows the lander to power the seismometer and also allows the seismometer to communicate with the lander. So we have the robotic arm up here. We're getting ready to deploy the heat flow probe instrument, HP cubed, which you can see right here. So the robotic arm has 3 joints that we use for the instrument deployment. We've got the shoulder right here that moves in azimuth, side to side, as well as elevation, up and down. We also have the elbow joint. It's right here. At the end of the arm, we have a grapple. You can see that the grapple is connected to the grapple hook on the heat flow probe instrument. Each instrument has one of those grapple hooks that mates to the grapple, which is like a hand or claw that allows the robotic arm to lift the instrument. So you can see when HP Cube is lifted, it also has a tether that goes from the instrument to the lander. That gets extracted out of the back. Oh, our deployment of HP Cube is starting now. You can see here's the tether I was talking about that gets pulled out of the support structure of HP Cubed. It's going to pause here. So the robotic arm's pausing here to take a picture with the instrument deployment camera, the one on the robotic arm. So that's some data that we'll want to have when we look and see how the deployment went when we get that data back on Mars. This entire sequence takes about 15 minutes. So it's going to bring HP Cube over the deck here and place it right here on the surface. So you guys should check back with us in a little bit and see how the deployment of HP Cube went. Back to you, Jari.
Okay. All right. Thank you, Jamie. So we're going to head into the question and answer period very soon. But first, we're going to have Bruce tell us something because he's got a very special little prop for you guys.
Yeah. So in addition to the science investigations that we're doing on InSight, we also have another experiment, and that is an experiment to see just how many people can participate in a Mars mission. So this is one of 2 chips that we put on the spacecraft, and these 2 chips hold 2.4 million names that were sent in to the InSight project. We advertise this opportunity in the media and over social media and ask people to, come to our website, put their names in, and we would put it on the spacecraft. And so this chip was engraved with a micro engraving machine. Each one holds up to about 1.8 million names, and we got 2.4 million people who are participating on it. These were both glued onto the spacecraft. Actually, they're right about here on the spacecraft deck right now, and they'll be going to Mars with your name on it if you signed up your name on the website. And so we're really excited about this, excited that people all over the country, all over the world, were able to sort of participate and go to Mars with us. And the other thing I wanted to mention that I neglected, I really want to give some credit to some of our partners. These amazing instruments that we have on the spacecraft are being supplied to us by some of our foreign partners. The seismometer is an instrument that was built in France, and the French Space Agency was in charge of it, but it actually had contributions from several countries, from Germany, Switzerland, the United Kingdom, and the United States. We all contributed to the seismometer instrument on InSight, and the heat flow probe was built in Germany by the German Space Agency. And this is really an international effort to go and understand Mars and understand our own planet.
Okay, all right, so we're going to now throw it open for questions. So as a reminder for the media on the phone line, if you want to ask a question, you press *1. We're collecting questions on social media at the hashtag AskNASA. And so I'm going to open it up for questions. Okay, well, I know that we do have a question on the phone line first, so why don't we get started there? So I have Sarah Lewin of space.com. Please go ahead.
Hi. Did you learn anything from Curiosity's 7 Minutes of Terror that went into planning for InSights?
Yeah, absolutely. Every time we do an entry and descent and landing phase of a mission, we learn something from it. Ours is much more similar to the Phoenix mission. We have the exact same type of entry, descent, and landing. Curiosity had a slightly different type of landing system that they used with their sky crane. But nonetheless, we learned a lot about how their parachute worked, how their heat shield worked. So many of the same phases of the entry, descent, and landing we learn from. We learn from every time we land on Mars, we learn something new. So we did learn from that, but it's actually a little bit more heritage back to Phoenix and even Viking.
Great, thank you.
All right, we have a second question. Actually, we have a question here in the room, so can we get a mic over to the reporter back there? Okay.
You said that you're doing this mission to learn more about our planet. What kind of differences does the atmosphere change? How does that factor into your experiment?
Well, for the science that we're doing, the atmosphere is not so important. We're really interested in the solid planet and the depths of the planet. Certainly in terms of the history of the atmosphere, the gases and liquids on the surface of the Earth and the atmosphere of Mars, they all originally came from inside the planet, from the deep mantle. And so those gases came out both through volcanism and other ways to get to the surface. And so by understanding both the composition of the interior and its thermal history, we'll understand better sort of the history of the atmosphere. One thing about the atmosphere is its evolution is also determined by the solar wind, because on Mars particularly, the solar wind actually can erode the top of the atmosphere. It kind of blows away part of the atmosphere. And so we could have had, or we know that we had a much thicker atmosphere on Mars early in its history, and it's been depleted by erosion of the solar wind. And one thing that can prevent that is a magnetic field, and of course the magnetic field is generated in the core, and so we hope to understand better the core and its evolution to understand when Mars could have had a magnetic field, whether that would have protected the atmosphere for part of its history, and maybe could have left Mars as a habitable planet maybe early in its history.
All right, we're going to go back to the phone lines, and we've got Stephen Clark of Spaceflight Now. Please go ahead.
Hi, thanks for taking my call. I have a couple of questions, one programmatic and one science. For Bruce, can you tell me a little bit about the confidence you have in detecting a marsquake? I know Viking's measurements proved somewhat inconclusive, but did they set an upper limit for what you expect to find? And also, if one of you can provide a total cost of the mission, and if you can, a total cost that includes the international contributions. Thank you.
Okay, so the level of seismicity, sort of the frequency of marsquakes, of course, is a really key ingredient into this mission, and we put a lot of thought into that. The first thing that you can look at is the relative seismic activity on the Earth and on the Moon. We put seismometers on the Moon back in the 70s for Apollo, and they measured something like either 12,000, 16,000 moonquakes, mostly very small, but still moonquakes nonetheless. And then we can compare that to the Earth, which is extremely seismically active, and guess that Mars is likely somewhere in between. And then we can look at faulting on Mars. So a lot of the ridges that you see, the canyons that you see, those are all caused by faults on Mars, and we can estimate sort of the amount of motion that had to happen on those faults, and that motion is accommodated by marsquakes, and look at that activity as a function of time, because we can put dates on all these faults and extrapolate that to the present, and you come up with an activity level that is, again, just kind of halfway between the Earth and the Moon. And so based on those calculations, and just based on calculations of the amount of stress that would accumulate in Mars's crust as it cools off over time, we can come up with estimates of the Martian seismic activity that we think will give us something of the order of 50 to 100 marsquakes over the course of the mission that we can see with our seismometer. And so using those marsquakes, of course, that's how we're going to probe the interior. Viking did have a seismometer. One of the seismometers on Viking worked. The other one, unfortunately, broke on landing. But the fact that that seismometer was bolted to the top of the spacecraft and didn't have the capability to pick it up with a robotic arm like InSight does meant that it was much less sensitive than the seismometer we're sending, and you can do a calculation on its sensitivity and conclude that unless Mars was more active than, say, the continental United States, that you probably would not have seen a marsquake. And so that does set an upper bound, but that upper bound is somewhat higher than what we actually expect today.
All right, we're going to actually go to some social media questions, so I'll throw it to Stephanie here.
Absolutely. So we've been having a very dynamic conversation on Twitter and Facebook and in our YouTube chat. Lots of questions for you. Aditya on YouTube would like to know, is there a plan for HP Cubed to have a retraction mechanism in case it encounters a hard rock? And if not, why wasn't it implemented?
We did consider that early on, but that would have increased the complexity, increased the cost past what we're capable of doing within our budget. So we did a lot of testing, and we designed it specifically so that it actually can tolerate some level of rockiness. So any rock smaller than an inch or so, maybe even 2 inches, the hammer on the mole is powerful enough that it basically just will push that rock aside in the soil. For a larger rock, if we hit a rock straight on, unfortunately that'll just stop the penetration, and we'll have to live with whatever depth we get. But if the face of that rock is inclined by, say, 45 degrees or so, the mole will actually slide down the rock and sort of redirect itself and go around the rock. And once it's left the rock, it'll tend to go back down into a vertical descent. And we're able to compensate for that in our calculations. So based on that and based on our calculations of the number of rocks that we expect in this area, that we can actually calculate from extrapolation of photos, we're pretty sure that it's going to be pretty low in rocks. We've actually picked sort of the biggest parking lot on Mars, and you can actually see any rocks bigger than about this in the high-resolution pictures from orbit, and you can go for kilometers without running into anything bigger than a football. And so we think that we have a pretty high confidence, or we have a pretty high confidence of the mole reaching down at least several meters, and perhaps all the way down to the 5 meters that we have as a goal.
Okay, next up from Conrad, will the data from the wind sensors and photographs be released to the public?
Go ahead.
Yeah, we will release all the data to the public. I mean, it's NASA's policy that the data that is acquired by NASA missions belongs to the world, belongs specifically to the taxpayers that have paid for it. And so we will be releasing our data. The plan is once we get the mission running and we get our pipeline in line, that we will get our data out within about 3 months of acquisition. We hope to release the photos even quicker than that. Again, once we have the photos in hand and have the processing fine-tuned for our particular place on Mars, we'll probably be putting out the photos within a matter of days of their acquisition. So you'll be able to go online and see what InSight saw on Mars not that long after we do.
And Shasta Robotics on Facebook asks, why hasn't NASA used Vandenberg for previous interplanetary missions?
Yeah, so I gave a partial answer a little bit earlier, but this spacecraft that we're flying was actually designed initially to fly on a Delta II rocket, which is a much smaller rocket than the Atlas V that we're launching on. And so with the extra capability that we have in an Atlas V, it actually allowed us to go from either the West Coast or the East Coast. For a variety of reasons, it's actually much easier to find a launch slot that we need for our planetary window on the West Coast. And so that was the primary reason that we chose the West Coast. And like I said, to break the monopoly that the East Coast has on planetary launches. As a California person, that was part of my motivation.
So we're going to go back to the phones for a minute, but I just wanted to follow up on Stephen Clark's question about the financial information, and we will get that to you from NASA headquarters, because they're the go-to people on the financial information. Okay, so next up we have Leo Enright from Irish TV. Go ahead, Leo.
Thanks very much for taking my question. I enjoyed the presentation at the mock-up lander, and I have a question about the TV pictures. But if I may first of all ask about data release, there are a lot of school children in Ireland involved in seismology and school programs who are watching every day data produced by their own seismometers, and they're quite excited that they might be involved now with the school's program involving Mars. So is there somebody on the panel who can talk a little bit about the school's integration? I heard you say 3 months. for data release? That seems like an awful long time if you're a school kid.
Okay, yeah, I can definitely talk to that. And in fact, we do have a direct connection with the seismometers in the schools program in Ireland, in the UK, in France, Germany, and the United States. And our plan right now is to stream the data directly to the schools, and in some cases, the schools might get the data even before the scientists on the team get the data. So we do have a very active program connected to the seismometers in the schools, and we hope to have students telling us where some of the earthquakes, the marsquakes are before we figure it out ourselves.
All right, we're going to take another question from the phone line. It's Amina Khan from the LA Times.
Hi, thanks for holding this briefing and taking my question. I have two questions. First off, you mentioned the interior of the planet is responsible for the atmospheric gases. Are there ways in which the findings from InSight and the findings from MAVEN will fit together or inform each other?
Yes, and we actually have are integrating our measurements and our science with all the previous Mars missions, but MAVEN in particular will still be, presumably will still be in orbit when we get there, and specifically the magnetic field experiment on MAVEN and our magnetometer on InSight can work together in order to be able to measure the magnetic field simultaneously at two different locations. And by doing that, we're actually able to do analyses of the magnetic field that are very difficult to do from an orbiter alone, because when you see the magnetic field changing in an orbiter, you have a hard time telling the difference between a field that's changing with time, or you're just flying through different places that have different magnetic fields. And so InSight will help MAVEN to be able to kind of unravel, that ambiguity. And with those two measurements, we can actually use the magnetic field variations to do another kind of probe deep into Mars. We can actually, by looking at the difference in the change in the magnetic field at altitude and at the surface, we can figure out what the resistivity of the electric resistivity of the material is as a function of depth. And you don't think of rocks as having current in them and having a resistance, but they do, and that resistance is related to their temperature. And so this is one other way that we can actually do a probe of the temperature variation with depth in the planet. And so this is something that we can combine with our measurement from the heat flow probe in order to better understand the temperature variations inside the planet.
All right, we're going to take, we're going to take another one question on social media.
Oh man, only one. There are quite a few questions out there, and everybody who's watching the live stream and submitting Ask NASA questions know that we will be hopping online and answering more with our subject matter experts after the live show. But I've got to bring out Inventor of Stuff, who asks, what is the best outcome or result you would hope to receive from InSight?
Well, I'll tell you, the first time we get a marsquake down on the surface, I think, I'm going to be dancing around the room, because this is something, when I was a graduate student, I was watching Viking, and there was a seismometer on Viking, and as a geophysics graduate student, that was like, the cool thing to do. And it was such a disappointment that we never got any seismic data down. And over my career, there was all these questions I had about Mars that could only really be answered with a seismometer. And so when we see that first quake, that's the final, underline, bold type, this is actually going to work, and we're going to start getting the kind of detailed information about the inside of Mars that we've been waiting for 40, 50 years. So
I'm not sure how I feel about you dancing, Bruce. I've seen you dance. I've seen you dance before.
All right, we're going to go back to the phones and the reporters on there, but we will take some more social media questions afterwards. So, okay, we are going to go to Elizabeth Howell of Seeker.
Hi, thanks for taking my question. I was wondering if, from any of the results that you'll be getting from InSight, if you can extrapolate anything about possible past or present Martian volcanism.
Yes, certainly. I mean, because the volcanism on a planet is tied to its thermal history, and it's also tied in many ways to the details of the interior structure. And so, for example, the size of the core will determine, well, there's a way the heat gets out of the planet, and it can either come out through conduction, which is pretty slow, or it can come out through convection, where the rocky material actually, hot stuff rises, cold stuff sinks, and pumps the heat out. And if the core is small enough, there's a boundary that appears in the lower mantle that keeps the heat from coming out. And so that would be something that would inhibit the development of volcanism. So we want to understand that. Another thing that is key to volcanism is the amount of heat that's generated in the crust as opposed to the mantle. And that depends on the partitioning of radioactive materials, thorium, uranium, and so forth. And that partitioning happens in this differentiation process that I referred to. And so instead of having these radioactive materials distributed all the way through the planet, they tend to be pulled out into the crust. And if they're pulled out into the crust, they deposit their heat as they decay in the crust, and that will affect the onset and the persistence of volcanism as well. And so, in addition just to knowing sort of the basic amount of heat coming out of the planet, which can be tied to magma formation and so forth, some of these more detailed structural issues that we want to address also will affect our understanding of the volcanic history of Mars.
We've got another question over the phone line. Ken Kramer of Rocket STEM, please go ahead.
Hi, thanks for taking my question and good luck. Two questions, if I can, please. One is talk about a little bit more detail about why you picked this particular location. Besides minimizing rocks, are there some science criteria that made you decide one site was better for collecting the data than another? And the other, you mentioned you have two cameras. Can you talk a little bit more about when we will get pictures from each of those cameras, and will you be collecting any descent imagery? Thank you.
Okay, I'll take the first question and let Tom take the second one. And so in terms of our landing site, this is kind of a unique mission in terms of Mars missions, because usually when you come to picking the landing site for a Mars lander, it's sort of a cage match with all the Mars scientists in the world, because if you're after something to do with the geology, the place that you go is key to figuring out what the problems that you can address are and what kinds of methods you can use for it. So, you want to go to a lake bottom, do you want to go to a volcanic flow? And so there's always a long drawn out process where, you winnow down the sites. For InSight, we have exactly the opposite situation, where we're interested in the deep structure of the planet. And anywhere you go on the planet, you're going to have the deep structure under your feet. And so it really doesn't matter. And you might think, well, you want to go to a place with more marsquakes, but that's not even true either, because what you want are marsquakes that are relatively far away, that shoot the rays through the planet and go deep into the planet before they get to you. So if they're very close to you, you don't really find out very much about it. So what we did when we put together the concept for this mission is I went to the engineers who were designing the landing system and the systems for surviving on the surface, and I said, you guys have a blank slate. You can go to the safest, easiest spot on the planet you can find, and I'll do my science. So just find a spot that's easy for you to land on, and I put easy in quotes here, and a place that you can make sure that this thing's going to last for at least a Mars year, because I need to be able to do my science. I need to be able to sit there and accumulate data over a long period of time. And so go to some place that's safe to land, and go to some place that is easy living, and that's what I want. And so they went through the process, and it turns out that with all the constraints from the landing system that we inherited from Phoenix and the constraints that we needed to last a long time, there were very few places on Mars that met all those engineering constraints, and this spot in Elysium Planitia turns out to be just about perfect for our purposes.
So I think what you're saying is that at least for InSight, it's what's inside that matters, not what's on the surface?
That's right.
Okay. All right, Tom.
Beauty's not just skin deep here.
Yeah, so just to add a little bit to that is one of the strong criteria we had is because we're the very first lander on Mars, stationary lander that's intended to last a full Martian year, 26 Earth months. Strictly with solar power, we had to land also close to the equator, so it was important for us to be able to get sun all Martian year. So that also constrained where we could land as well. To answer the question about the images, on the very first day that we land, we'll take an image with our context camera. That was the one that's mounted under the deck, more or less about here, underneath the deck. That'll take a picture of the workspace in front of the lander where we intend to do the deployment of the instruments. So that'll give us an idea about how easy or how difficult our job's going to be over the next few months. And that'll be available, like I said, probably the very first day that we land. Very quickly after that, we'll be taking an image with the camera that's located on the arm, the instrument deployment camera. That first picture will actually just be of like the arm itself. We need to check and make sure that it looks okay. Eventually, we'll unstow the arm and start taking pictures of the workspace in more detail. And we have a plan to do a panorama of the area that's around the lander. Don't know exactly what sol will do that. That's not a priority science item. But as soon as those pictures are taken, we're going to release them as quickly as we possibly can.
Okay, we're going to take one more social media question, and then we're actually going to go back and look at the test bed and see what's happening there. So, Stephanie.
All right. So we have had quite a bit of conversation about potential humans to Mars. A lot of people sharing excitement, and they want to know how will InSight help inform potential future human exploration of the red planet.
Yeah, so it's a good question. It's one that we often get. What we didn't talk about, what is also on the lander, is we have a bunch of meteorology experiments. So we have a pressure sensor, a wind sensor, a magnetometer, and those are all actually there. The main reason is to support the SEIS instrument. The SEIS is incredibly sensitive. It's good at detecting everything in the environment as well as marsquakes. And so we have those sensors really there to decorrelate the noise from the environment from our seismic measurements. But they're also going to give us very good information about what the weather is on Mars at that particular location. Also understanding what the change in the magnetic field and the atmosphere is important to understand for future people that might go to Mars. So I think basically understanding the weather on Mars is probably the best tie-in there.
So let's go back to the test bed then. Jamie, can you tell us what's going on there?
Thanks, Jerry. Yeah, welcome back, everyone. So we've successfully deployed the heat flow probe instrument here to the surface. So now you can have a better view of our instrument deployment camera, which is right here on the robotic arm, and also maybe a better view of HP Cubed and its engineering tether that's been pulled out across the lander deck here. So now you can see HP Cubed is still grappled by the robotic arm. What we're going to do on Mars is we're going to look at these pictures with both of our cameras, see that HP Cubed or SEIS or WTS are safely on the ground, and then on the following day we'll release the grapple. So the grapple is a hot wax actuator, so it heats up and then the fingers slowly expand and then the arm comes up a little bit, and that's how we release it. And at that point then the heat flow probe is on the surface and ready to begin hammering. We release the mole and it'll hammer into the surface and start its science. So that's all for the update here. If you guys have any questions about the testing, let us know. Back to you, Jari.
All right, thanks. Okay, so we're going to start wrapping up here, but I wanted to let you guys know about ways to learn more about InSight. So one thing that's special about InSight is that we actually have a Mars Roadshow. So people can't actually get to Mars, but for those of you in California, we're going to try and bring Mars to you. So we are also going to provide some details about how to watch live in case you happen to be in Central California, and hopefully it's not a foggy day. You can actually see the launch. We have some details on that and the roadshow at mars.nasa.gov/insight. We also have all the news about the mission there, as well as a link to the press kit. And another website that you can go to for more information about InSight is nasa.gov/insight. Also, of course, we've got social media, so please follow the mission and join the conversation at NASA InSight on Facebook and Twitter. Also, just following the conclusion of this press conference, we're going to be replaying the images and videos. So thank you to everyone for coming to learn more about InSight, and onward to Mars.
Some of the parts were produced stuff.